Today we're going to be looking at the angle of friction. Now, the angle of friction isn't actually in the Cambridge syllabus for A level, but it's something useful. It draws upon Lami. So let's think about what friction is made up of. Let's get the change the colour on my pen so I can actually see the. So, if we remember, we have our contact force, our friction, and our total contact force C. And it's separated, if we draw a right angle triangle, we can consider it as being separated by this angle, which we're going to call lambda. And this is the, lambda is the angle of friction. So the whole idea is if we consider the total contact force, the normal contact force and friction as one force, i.e. the total contact force, and it acts with angle lambda, where lambda is the angle of friction, then we can use Lami's theorem to make calculations simpler. So let's consider this. Let's consider a simple situation where we've got some box and it's on a slope, and we pull it with a string at some tension T, parallel to the horizontal, so therefore friction is going to act in this direction, and we'll have the contact force up the way and the weight acting down the way. So we can consider our consider the contact force, and we consider friction, then the normal contact, the total contact force is going to be acting in this direction at some angle lambda. So let's redraw our force diagram. So we've still got our tension in this direction, we've still got our mass down here, but this time we have C, the total contact force, acting at some angle lambda. Now let's consider this. If we consider just some simple trigonometry, the tangent of lambda is going to be equal to friction over the normal contact force. The r's are going to cancel, so what we have here is the angle of friction, lambda, is going to be equal to the inverse tangent of the coefficient of friction. So this is an important. It's important to remember if you're going to be using this to solve problems. You don't need to use the angle of friction or Lami's theorem, but it can make things a little bit simpler. So now let's consider the situation where we have a box on a slope. And we're going to say this angle of the slope is called lambda. You might be seeing where we're going with this, but for the minute this is just the angle that we decided to call our angle that the slope makes with the horizontal. And we've got our box. In the vertical we've got the weight, and we've got some, and this is we've got the friction acting up the slope. So this is in limiting equilibrium. So that's important. It's in limiting equilibrium. And perpendicular to the slope we have R. Now what we find is in the case of limiting equilibrium, we have our weights down, but in limiting equilibrium the total contact force C acts is an opposing force to the weight, because it's in limiting equilibrium, these two forces must cancel out the weight of the box. Therefore, if we consider the components of the total contact force, this must be lambda, or angle of friction. Now let's look at how we can use this to solve a couple of problems. So a man tries to drag a suitcase of mass 18 kilograms along a rough horizontal surface. He drags it with a rope at angle 20 degrees above the horizontal. The coefficient of friction is 0.4, and the suitcase is in limiting equilibrium. Find the tension in the rope. So let's draw our force diagram. Here's our suitcase. We know the mass is straight down, so it's 18g, and we have, there's a horizontal, we have this rope with tension T, and that is at 20 degrees to the horizontal. Now this is straight up. This would be our normal contact force, but remember we're doing C, and this angle here will be the tangent of the coefficient of friction. So remember, lambda equals inverse tan of u. So let's consider our using Lami here. wrong way. So we've got 18G. We have T and we have C here. And this angle here is lambda, and this angle here, that's going to be right angle, and this angle here is going to be 20 degrees. So remember, I'll just remind you, Lami's theorem is if we had, say, A, B, C, well this is angle alpha, this is angle beta, and this is angle gamma. A over sine alpha, I'll put that underneath here. A over sine, A divided by sine alpha is going to equal B over sine beta is C over sine gamma. So we want to find T. So T over this angle. Now what is this angle? So that's 180. So it's going to be sine of 180 minus what lambda is. And we know this angle here, so that's going to be, we know this angle, we know what we can work out this here, so we'll do 18G over sine, so what is this going to be? So this is 90, this is 20, so we'll have and this is lambda. So 180 minus 90 minus 20 is going to be, that'll be 70. So this angle here will be 70 plus lambda. So rearranging everything, we will get T is equal to 66.9 newtons. Let's consider another one. So a 2 kilogram brick is at rest on a plank. The plank is lifted to an angle of 20 degrees with the horizontal. The brick remains stationary. Find the total contact between the brick and plank. So we'll have the situation where this is 20 degrees. Here is our brick, and we have, this is 2G, and because the brick is stationary, the total contact force must be equal to the weight in the opposite direction, so C must be equal to 2G, which is equal to 20 newtons. So next thing we want to work out is the plank is lifted to 25 degrees and the brick is at the point of slipping. Find the coefficient of friction. So again, we have 25 degrees, we have our brick, 2G, and C is still up here, and the angle that C makes to the contact force will be lambda, and lambda must be the same as the angle of the plank because it's at slipping point, so lambda is 25 degrees. So the coefficient of friction must be the tan of 25, which is 0.466. Now we are going to imagine the plank is lifted a further 10 degrees to 35 degrees with the horizontal, and the brick is held by a force at an angle 15 degrees above the angle of the upward slope. Find the size of the force. So this takes a wee bit of thinking about. So let's consider our force diagram now. What does it look like? So we've got our, now it's now been lifted another 10 degrees. So this is now 35 degrees. I'm going to move this up a wee bit more so I can just get a bit more room. So here's our brick. And down the vertical we've got our 2G. Now horizontal parallel to our slope here, we've got some rope and it's got some tension and it's at an angle of 15 degrees. Now if you think about it, up here our coefficient of C, our total contact force, was along the vertical, but now this is our vertical and the total contact force will now be knocked off by an angle of 10 degrees. So that is C, and our perpendicular, this is our perpendicular, so this here would be our R, and that is still at 25 degrees to our C. And that is because it's still limiting equilibrium, because we've got this force, we'll call it tension T, it's still in limiting equilibrium. So the angle of friction between C, the total contact force, and the perpendicular slope is the same as what it was in the previous problem. Now what we're going to do is we're going to take the angle, the forces C, T and the weight, and we're going to put them into a force diagram. So we'll consider, we've got down here our 2G, our weight. Now, if this is our vertical line, C is going to come up here, and that is going to be at 10 degrees. Now let's think about something that's easier to, we need to think where is, we're going to have our tension T here, but we need to think what is this angle in here. So the angle here would be, well, think about the angle is 15 here, and that is that's going to, if you add, you can work at this angle here, add to the 15, and we're going to get that as 140 degrees. So this means that this angle in here must be 40 degrees, which gives us this angle over here as 130. So now we can use our sine rule to work out t. So t over sine of 10 must be 2g, which is this vector, over sine of 130, which if you work all that out, you'll get t is equal to 4.53 newtons. And again, the trickiest point of this question is being able to take your force diagram and put it into this form. So I hope that helps.